Now that we've covered the basics and the easy part of fluid mechanics, the fluid statics, let's really start looking at the fun stuff, and that's fluid dynamics and when fluids are moving. Now, unlike a static system, where in strength of materials or whatever, you would sit there and go, well, there's a block of material, and I pull on it, and I can calculate the stress out there. The problem is we don't have a solid chunk of material. We have something that's constantly flowing. And so we have to kind of change the way that we're going to look at problems, because we can no longer look at a chunk of mass and deal with it. So what we're going to do is we have to look at things in a slightly different way. So we've got three ways to solve arbitrary systems of moving fluids. We can use a control volume analysis. This is what we use on a larger scale. This might be similar if you've already taken thermodynamics to the thermodynamics that you've taken a look at. We can look at it at a differential analysis, which is a smaller scale. This is where we're using differential equations and things like the Navier-Stokes theorem to calculate out what's going to happen to fluid flow. And then we have experimental or scalar analysis or non-dimensional analysis or model analysis. It has a lot of different names. This is the analysis, this is what they do with wind tunnels. This is where I can take a little bitty plane, stick it in a wind tunnel and go, well, this is how the massive big thing's going to work. A majority of what we're going to do is we'll be doing control volume analysis. Differential analysis, that's really left for the kids that are taking the fluid dynamics class. We will do some scalar analysis when it comes to pumps, especially when it comes to sizing of pumps. So the first thing here is I want to talk about Ludwig Prandtl. The entire concept of control volume was developed by Prandtl. He is a very big deal within the fluid mechanics community. He basically is the father of modern fluid dynamics. And everything that we're going to do is basically kind of based off of a lot of the stuff that he did. There is a Prandtl number, and it's actually dealt with a lot in convection heat transfer, which is the heat transfer of fluids. Now, to apply this to a control volume instead of a set piece of material sitting in there, what we do is we end up looking at a couple of equations. Now, these are equations that you should be familiar with your your physics classes: conservation of mass, or conservation of matter, conservations of linear and angular momentum, and conservation of energy. So we're going to apply these equations to a control volume. Now, just a couple of things off the bat. We need some vocabulary. So let's vocab time. So we're all on the same page when we're talking about different things. And when we're dealing with a control volume, we have three important topics that we're talking about. The first is what we call the system. So what is the system? The system is the arbitrary quantity of mass of fixed identity. Basically, this is what we encapsulate within the control volume. This is everything inside the control volume. Second thing we have is the surroundings. What are the surroundings? Well, the surroundings are everything outside of our control volume. And the last thing that we worry about is what we call the boundary. The boundary is that control volume itself. So we end up drawing a control volume around the system, and we separate the system from the surroundings with a boundary. And a lot of the things that we're going to be looking at when it comes to solving these equations through a control volume is what's piercing the boundary, what's going from the system to the surroundings, what's coming from the surroundings to the system. And that's really going to drive everything that's going on. Now, out of these, conservation of mass, linear momentum, angular momentum, conservation of energy, we're not really going to worry about angular momentum in this class. We're going to be more concerned with the other three. Angular momentum, yes, it's a little bit different from our linear momentum. We get into some cross products and stuff, so we're just not going to cover it in this class. So before we can really talk about what's going on in the control volume, we have to worry about, well, how do we change those equations over so we can actually use them. So we can use them on a flowing system and not just a static system. And so we pop back to Osborne-Reynolds. So this is the guy that gave us Reynolds number. Also gave us something very important, which we call the Reynolds transport theory. So Reynolds transport theorem is basically a way of converting over equations that are specifically for individual masses to apply them to a region of space. And this region of space we will call the control volume. Now, there's a lot of math behind Reynolds transport theorem, or sometimes you'll see it written as RTT. It's a little beyond the scope of the class, so we're not going to really worry about how we mathematically transfer those equations. We're just going to start right with those equations. But before we get into those Reynolds transport equations, what we need to do is we need to look at the couple of different ways that we can analyze a velocity field. And they really come down to two different viewpoints. The first is what we call the Lagrangian method. It comes from Joseph Louis Lagrange, who was once again one of these fluid mathematicians. And he came up with a lot of actually celestial mechanics, which is mechanics of orbital bodies. And this is why you might have heard when they talk about satellites about Lagrange points and whatnot. It all comes from him. And so what it is the Lagrangian method of solving for fluids is we take a look at one fluid particle and we track it wherever it goes. And so we look at it at each individual point and we take a look at that just one individual particle and solve basically F equals ma for each particle, for each point the particle is in. So the motion of one particle is insufficient to describe the flow field, so motions of all particles have to be considered at the same time. And as you can think about it, within a field there's going to be a lot of particles. That'd be very difficult to do those all simultaneously. And because we're looking at each individual little thing, we're no longer really using that continuum assumption where we're talking about all those spatial gradients or even through things. We have to look at them at very individual little points. Thus, because of this, the entire Lagrangian approach is really only used in special circumstances, and we are not going to be doing that in this class. The way that we're going to look at things is we're going to look at Euler. So Euler was a Swiss mathematician. He did a lot of neat mathematical stuff. And you'll notice right down here it says known for. Well, there's way too much to list because this guy was a mathematical genius, came up with just tons and tons of things. So you've probably heard of Euler factors and stuff in your different classes and whatnot, especially your math ones. So what we do with the Eulerian approach is instead of focusing on an individual particle, we focus attention on a fixed point in space. And so we just sit there and go, okay, well, this is what I'm going to look at, and the particles are going to go through that point, but I'm just going to focus on what's going on in that little point. And so then what ends up happening is you focus your attention on a fixed point in space, and then you can start looking at vector components of what's going on. So this approach is by far the most useful, since we're usually only interested in the flow field in some regions and not really the history of the individual particles. It really doesn't do anything for us to track individual little particles. However, the problem is we've got to transform these F equals ma equations from single particles to a control volume. And this is where Reynolds transport theory will come in, so we can do control volume analysis, very similar to thermodynamics. So in converting these, we have to now, instead of using the Lagrangian approach and applying our equations to one little particle, we have to convert to this control volume analysis. So the math is applied to regions instead of individual particles. Now, in order to do that, there's a generic form of Reynolds transport theorem that allows us to convert these equations over. And typically there are 7 classical ones that we end up doing: mass, linear momentum, angular momentum, energy, entropy, And actually that's it. So there's 6, not 7. We're not really going to worry so much about the general form. In the next video where we're talking about conservation of mass, I will talk a little bit about what the general form is, and I'll show it to you, and then we'll just build the equations off of there. But a very important thing that we're going to need is that control volume. So the next lecture we'll talk about that control volume, and then we'll roll into everything else.